ngana tukwata electrical schematic, and then we managed to create the PLC program. The most obvious question is, how are we going to simulate our program? How are we going to ensure that the program works the way it's supposed to work? Okay. Now, kwadibama ways aengi in which this can be achieved, but just to spice things up, to allow wonfia factory IO. Okay. Na factory IO ndela ndapo ni hii program hii. Factory IO version oyonkwete ni version 2.55. So the program, it provides more like a virtual plant yakweba titwa wulamo ama inputs napakubala twala chita so twala wule itulela ndati A to B as a reference, and then the only thing if twala chinjako twala isa pama operators tuwule ko don't even know what this is called. It's a column. Okay, so this is actually a column. I was going to call it a pole, but it's a column. So ngatuabula a column, then tualabula na box. Now this box is similar to that box for the electrical components, the components which would make up things like this control circuit would be enclosed within such a box as this one, maybe bigger, but it's the same concept. Okay, nga tuawula I box tuaingisha mudi factory IO. Our interest is in ensuring that tulefua ko the emergency stop, tulefua ko ibale about emergency stop. And the reason I'm bringing this out is so to appreciate the way these input conditions are going to be interchanged between the Siemens Step 7 and the factory IO, so that we know what's in the background. So to abula ko emergency push button, and then to alabula kona a normal system stop like this. To alabula kona system stop. Where do we put this? Is it on the face of the box, I wonder? Okay, it's a bit off. Let's turn that. Now I think it is on the face. Okay, yes it is. And then E to shako lubadiko right, then this one to allow wulako iseleleko pamoro. Okay, then to wule na start push button, which I think is the what is this one? The start button here. Then move you to the face of the box, okay, like so. Then we may also want to take a reset button, put it right about there. Okay, so let's look at the actuators and the operators. Okay, so this is what we have. So here we have sensor tags, and then we have actuator tags. Okay, sensor tags, and then actuators. We may want to rename these. Okay, instead of having start button 0, we're just going to have start. Okay, we're going to just have start, and then here we're just going to have stop, and then this one, for now we just call it emergency. I'll just do the shorthand EMR just to represent the emergency push button. And then for the reset, we just call it as reset without the button, okay, without the button part. And then of course I don't really need the lights, so we can just do away with the lights part, okay. So this is what we have. So now that we have these components brought onto the face of our box, our electrical box, this is no different from a situation where you have something like this, and then all these components are within a box or a panel, if you like. So whereas we can have the system start, we can have the system stop, and we can have the emergency push buttons, and do we have a reset? Okay, things like the fault reset. These would be emulated by these buttons, right? So having done this, the only other thing we're going to do is we're going to go to drivers, and then of course we're going to choose Siemens S7 PLC SIM, and then we're going to be asked, okay, as at now it assigns the default addressing, like the addresses for inputs will start from input 0.0, whilst the outputs also start from Q 0.0. But we can change this to, we come where it says configuration, and then here where it says, okay, we may want to mark in the auto connect, so that when the PLC SIM is online and you open up the factory IO, it will just basically auto connect, just like the checkbox says, okay. Now on IO points, you notice that we're being asked about the offset. Offset is essentially the starting address offset. So in our case, maybe we just start from input 0.0. Now we'll start from input 1.0, okay. So the offset is going to be 1, and then the number of inputs, the count, okay, the number of inputs, we've taken in 4, okay, the start, the stop, the emergency, and the reset. So the number of inputs we are interested in need 4, okay. For the Boolean outputs, we're going to start with 4.0, Q 4.0 as the first output. So the offset is going to be just that 4 as the offset, and the number of Boolean outputs that we were interested in. What do we do with this? Do we want 1, 2, 3? Okay, in this particular instance, we'll just maybe pick just 1, okay, just for illustration purposes. And then having done this, okay, I know, you notice that now the input addresses start from input 1.0 all the way to input 1.3, okay, and then of course just one output. The reason why I'm showing you this is because if we've been using memory bits to create our logic, but you notice that in this interface, factory IO provides exchange of data between PLC SIM and the software itself by way of physical inputs and physical outputs, whilst we've been working with the AMA memory bits. Okay, so now the question is, how do we make this work for us? Okay, which is why we're looking at this. So this is the project that we've been working on. Okay, this is just Part004 as the original project for the crusher. So now that we're here, what we're going to do is we're going to go into the hardware configuration. Okay, because we never had the physical input modules by way of input modules and output modules. So twalaisa kuraityoku, for the profile it's just standard. Okay, so we come under Cymatic 300 because the PLC CPU that we're using is a CPU 315 2DP, so it belongs to this Cymatic 300 part category, right? And then we're going to come to where it says SM300. then to allow my digital inputs, because we're not really going to download our project to an actual PLC. We can pick any input module we want. Okay, so apa na lasenda via SM321 48 to 125 VDC. Oh, okay, there's no harm. 16 inputs. Okay, so we pick this one, and then we may want to pick another one. We'll pick another one of the same type, which gives us 32 inputs, which I think is adequate. But just in case, we can pick another digital input module. Okay, so now we have 3 digital input modules, and then we're going to pick a digital output module. Okay, digital output module. Voltage 45 to 120 or whatever. So let's pick which one. 16-bit digital output module. I think we just need one of these because we don't really have a lot of outputs. So having done this, if we look at this section at the bottom, okay, you notice that the start address and the end address for each module has been automatically assigned. Okay, so you notice that for the first digital input module in slot 4 is starting at 0.0 all the way to 1.7, and then the next digital input module is starting at 4.0 all the way to 5.7, and then the last digital input module in slot 6 is starting with address I8.0 all the way to I9.7. Okay, even though there are bits all over the place. So what do we do? I would want to start with digital input 1, digital input module with an address of 1.0. So okay, object properties, addresses, system default, no. I want to start at 1. Okay, obviously I'll end at 2, obviously, and then I would want to start for the second digital input module. I would want to start at 3. Okay, I would want to start at 3, obviously end at 4, and then the last digital input module I would want to start at 5, right? I want to start at 5, end at 6. And then for the digital output module, I want to start at 4, obviously end at 5. Okay, so now this is sorted, right? But the only critical thing to pay attention to is that I've actually also created a Profibus DP master system. Because what I noticed is if you rely on the MPI, if you rely solely on this MPI network, okay, if you rely on the MPI network, okay, or rather subnet, because you usually find them under this subnet category. So if you rely on this MPI subnet without the Profibus, then factory IO in my case wasn't really connecting to, or rather it wasn't exchanging data with the step 7 by way of the PL system. So it's better maybe you include the subnet Profibus, okay, so that at least you don't really get the runaround. Having said that, okay, the only thing we have done is that twaingisha mwama physical input modules na physical output modules. And I know you may be thinking but wala chitashana assign ama addresses because previously we had this symbol table already imported. We had this where we've got all these addresses already imported. And then if you look at this, to quite a few memory bit addresses, there are no physical input module address or physical output module addresses. Okay, so this is what we're going to do. we're going to move on to just illustrate the exchange of data between step 7 and Part004. So essentially, this is system start. Okay, so system start is associated with memory bit address M10.0. Okay, so we're going to copy this. Okay, this is a memory bit address, and then in here, when I say edit symbols, if I say, okay, what's your problem? Because the symbol table is already open. Maybe I may want to close that. Edit symbols. Okay. If I say system start, like so, okay, I'll say PI, which is just peripheral input, meaning I'm making reference to the actual physical input modules. Okay, that's why the original tag I created was for system start assigned to a memory bit address, PI. Okay, so now here the only thing I'm doing is, as opposed to having to create separate tags for the same thing, because these are essentially just going to reference the same control aspect. So system start, but now this is a physical input, okay, external to the program. This is expected to be the one which gives its state to the memory bit address M10.0 for system start. Okay, I'm just adding PI just to remind us that it's just system start, but associated to the physical input module. Okay, and then for the next address, okay, let me just save this and then close, then go back to the symbol table so that we are together in this. Okay, we're going to look at system stop, which is right all the way down here. System stop is here. Okay, so system stop is assigned to memory bit address M10.1. okay, so this is a memory bit address, but now I need a signal, a physical input signal, okay, which is going to be sent to the PLC by way of the digital input modules. Okay, so I'm going to copy this tag here. Okay, then I'm going to come here again, edit, and then I'm going to come here, paste, add PI, just peripheral, or rather peripheral input. Okay, of course it's Boolean. Apply this, close, and then of course we saw that we have the emergency. Okay, we have the emergency push button, even though in this case we have several of them. So emergency station 1, emergency stop. So we're going to copy this, and then we're going to come here, edit symbol. We're going to do that, add a PI at the end, peripheral input, it's Boolean for a data type. And then of course, what else do we need? We have the system reset. I do believe we have the system reset. So system reset is right about, okay, system fault reset. We're going to copy that, and then edit symbols, and then PI at the end. Okay, and then the last one, we need a driven load. Okay, but so we've got the system start, system stop, station emergency stop, and then system fault reset. I think we're done with this part, and then we need to drive a load. Okay, so we go to the digital output module, and then of course, what can we pick? How about the siren? In that case, we've got a conveyor. Okay, we can always change it. Symbol table, we had the pre-start warning alarm. Okay, do we have it here? Pre-start. Okay, pre-start warning alarm. Okay, where are you? Pre-start siren local address, which is right about here. Okay, so local station, pre-start warning alarm, or rather siren, which is assigned to memory bit address M100.3. So we go to the digital output module, edit symbol, and then okay, can reassign this to Q4.0. Okay. Q4.0. I don't need Q4.0. Okay. Don't need Q4.0. So it's Q4.0. It's right about here. We just change this to this, and then we just say PI. We save this. Okay. Pre-start warning siren assigned to physical output address Q4.0. Okay. So save that and close this. Okay. So you notice that there are actually different locations where we can change these addresses, because we were just changing it from here, but we have changed it from the symbol table. Same difference. Okay. So now this is done. So the only other thing we need now is do we talk about mapping? Okay, let's create a sample logic. Okay, let's create sample logic. So insert function, insert new object, insert function. Okay, and then we're going to call this as come on. We're going to call this as sample logic. FIO for factory IO, and then the language, let's stick to ladder. Okay, and then when this is done, we're going to open this. Okay, going to open this, and then of course we know that we've got the start, stop, output coil, parallel branch, seal in contact, close, and then we can have the fault reset in series. Okay, but I don't really know the state external to step 7, as in the state of the reset push button in factory IO. That we're going to find out. Okay, so this was I 1.0, I think, and then this one was I 1.1 for stop, and I believe this one was I 1.3, and then the output was Q 4.0. Okay, and then of course we'd sail in through this. Okay, so this is how this would look if we were just using the physical addresses. Okay, like if we limited ourselves to physical input addresses and physical output addresses, the logic would pretty much look like this. But it's not what we have done, is it? So what we have done ourselves is we've used memory bit addresses. Okay, we've used memory bit addresses. So our logic looks like this. Okay, so this is system start, memory bit address. Okay, and then of course system stop, memory bit address, and then system port reset. Okay, and then pre-start warning siren, PSW pre-start warning siren. Okay, like this. And then we seal in through this. Okay, so this is how our logic looks like. Okay, because we've been designing everything just using memory bit addresses. So this would pretty much look like this. Okay, so we'll get rid of this first network because it's not the way things are. So save this. Number, the same thing we've been saying. This function, itwapange function 3, it won't do anything if it's not been called in OB1. Okay, so we need to open OB1, and then we need to call this function 3. Okay, and the function sample logic. Let's save. Okay, now we're good to go. And then we may want to simulate this just so we know everything is the way it's supposed to be. Okay, so our preferred connection point, Yalaba Profibus connection. So let's pin this, and then we'll get into running P. Then we're going to download this project to PLCSIM. Okay, I believe that is done. Okay, we're good to go. So we're going to open this function 3 that we have created. Then we're going to monitor this. Okay, we're going to monitor. So to control this output, or to control the siren, the pre-start warning siren, we have to modify the memory bit address allocation M10.0. We modify this to 1, then we modify it to 0, and then it seals in through this path. Okay, then to stop, we modify the system stop. So in this particular case, what we don't really need the fault reset, but just to stop, this is just so we see the behavior of these inputs, okay, when they've been passed on from factory IO. So when we modify the system stop to 1, modify it to 0, the siren is de-energized. Okay, so now that we know that these are memory bits, okay, there's such a thing as mapping. Remember, we can pass a physical input signal state to a memory bit address. Okay, so what I mean is we can pass, we want to say and I 1.0, which is the system start. We're going to pass the signal state of this bit, or rather address. We're going to pass it on to this address. Okay, we're going to pass it on to this address. So copy, we're going to pass it on to that. Okay, and then the same thing for system stop. So and I 1.1, we're going to pass the signal state to memory bit address 10.1, and then we're going to pass the signal state of I 1.3, I think. We're going to pass this on to memory bit address 10.7. But for outputs, okay, for physical output addresses, okay, we can only pass the signal state of a memory bit to that physical address. Okay, so what I mean to say is we're going to pass the signal state of memory bit address 100.3. We're going to pass the signal state to Q4.0, okay? So is equal to Q4.0, like so. I think this covers every aspect of this, okay? So now these addresses can lend themselves to factory I/O manipulation. So now we're just going to configure the connections, okay? So we go back to the drivers, okay? So now you see that the Siemens S7 PLC SIM has been detected. So the only thing we need to do is assign the inputs, okay? So start Moody program, yes, Moody step 7 was assigned to input address 1.0, the stop to input address 1.1, and then what? Reset 1.3, emergency stop. Am I right? Or is it the other way between these two? Goldfish memory. Goldfish memory. I think I've mixed up the system reset and the emergency, okay? I did not even use it here, okay? System stop. We may want to station, so it's station 1 emergency stop, okay, which is 1.2. Emergency stop. So which makes this 1.3, which makes this 1.0, 1.1, 1.2, 1.3. So it has to be the other way between these two, okay? Emergency, this has the right of 1.2, it should be there, and then the reset is 1.3. And then on the output side of things, I know Moody program, yes, tulandela pre-start warning siren, but in this particular case we can even use the conveyor, okay, as just an illustration. So when we have these, you notice that where the light is on, it shows that the normal state of this is a true state. Think of this section as our PLC. Okay, think of this section as our PLC, the box thing as our PLC, the physical input module combined with the physical output module. You notice that when the light is not on, meaning the state of this is false. Okay, let me just try to click on this. It's in the run state. Okay, let me put this in run, maybe. Then let me zoom in. Then let's go back to drivers. So what I meant was, if I press on the start, you notice that the light comes on. So meaning the signal state at input 1.0 is true. So true, false. Emergency push button actuated, the light goes off, reset becomes true. Okay. The same thing with the system reset. True, false. So mwamonati, the start na reset, their normal state is false. Whereas the system stop and the emergency, their normal state is true. Meaning that if these were actual physical devices, if this was a physical device, the emergency push button, we would use a normally closed contact of this. And so the same thing goes for this, for the stop, with that we'd use a normally closed contact of the system stop push button. Meaning this unit has got a block at the back with auxiliary contacts. We'd use the normally closed contact of that. Okay. So that said, and then of course you may ask, okay, what is the difference between the emergency push button and the system stop? If you noticed here, okay, if I press the emergency push button, it sustained the change in state, okay, unless of course I reset then the status is normalized, as opposed to a push button, the normal system stop. Once I release, even the signal state resets. Okay. So now that we have done this, we can just go back to step 7. Okay, we can go back to our project, which is right about here, and I think what we need is the mapping. We can look at the mapping in relation to this logic. Okay, so we can window arrange tile vertically, then we don't need the overviews maybe. Okay, so let me just push them a little bit like so, and then let me move this a bit to the left. Function 3. Okay, so this is our function 3, and then we want to look at this in relation to this. Okay, we want to look at this in relation to what we have done in Factory.io. Okay, so system start, you notice the change in state. So what is happening is Factory.io is passing its signal state for the start push button to the physical address, input address I1.0. okay, because if you notice where it says status here, okay, status, this bit here, okay, if I press, it becomes true, false. Okay, release, false, press, true. Okay, so that's what's happening there. So to make our pre-start warning siren to be energized, we need to correct the signal state of this. Okay, so you notice that as at now, the system stop is showing that okay, we need to reset this. Okay, because we haven't mapped it here. Okay, this is not mapped, so I need to borrow this, then I need to come here and then pass your signal state now. And I1.2, was it 3? Okay, no, suppose it be I1.2. okay, I1.2, pass your signal state to this bit address. Okay, like so. Save this, download. Like so, so that now this is a true reflection of what is happening. So like I was saying, in this Factory.io is passing the signal state of the start push button to this address, which is I1.0. In the same way, Factory.io is passing the signal state of the stop push button to this physical address, designation I1.1, and then the signal state of the emergency push button is being passed on to this physical input address I1.2. okay, and then lastly we've got the fault reset, which is being passed through input address 1.3. okay, so Factory.io passes its conditions through the physical input addresses, okay, and then it will only accept output addresses, physical output addresses, not memory bits. So the only thing we're doing here is that we are passing the signal state from these physical addresses by way of these input addresses and output addresses. We are passing them on to the memory bit address, okay? So all we're saying is the physical input condition is being passed on to a memory bit address, okay, except for the outputs where you've got the condition of the memory bit address being passed on to an output, a physical output address. So this is how just these work, okay. Now for you notice that right now we cannot start the siren, okay. We can't simply start it because it's open at the position of the system stop and it's open at the position of the emergency stop. So if we wanted to retain this configuration, we need to change something here, okay. As opposed to saying and, we'll say and not, okay, and not here at the system stop and also at the emergency stop. So we'll save this and download so that we correct the problem, okay, like so. And then when this is done, we can easily start the siren, or in this case we can now start the conveyor, okay, because that's the one which is holding the address. So if I do this and then I press the system start, you notice that we're able to start the conveyor. Stop, we're able to stop. Start, we're able to start. Stop, we're able to stop. Or start, we're able to start. Emergency stop, we're able to stop. So that's the state of this. And then of course, to test the reset that is being brought in this correct state, you notice that there's a change in state of this memory bit address. So this is how these variables or addresses are passing on data, okay. Now the reason I prefer working with memory bits is I don't want to be tied down by physical addresses. That way, if you need to change or reallocate the addresses, you can easily do that, okay, because there are instances where Mazasangati, maybe by the digital input module, a position is not working, okay. Not the whole module is not bad, just the whole input module or output module is not bad, but just one position is wrong, okay. It's not working the way it's supposed to work. In this case, as opposed to kufunyapo fechonse chi module mwabika po chi input module chi output module mwabika po chimbi, you can just simply reassign the input to another address or another location on another input module or output module which is not occupied, okay. This works to our benefit. And also, if we work like this, you notice that we're not really bothered with having to configure the hardware before we start the program, okay. So that's the benefit of doing it like this. I hope this whole factory IO will pass its signal state to the physical input addresses, and then these physical input addresses are going to pass their state to the memory bit addresses which we have used in our logic. So basically, when it comes to simulation, every identified input will be brought into factory IO so that to signal states, so that it's easy for us to simulate. And also the beauty of factory IO, as just as a by the way thing, you notice that it also has these funny alarms, okay, like warning devices. You have siren, okay. If we wanted that pre-start warning siren we were talking about, we could just come here like so. So now that we have a siren, we could go to file, drivers, and then remove this conveyor, put the siren there, okay. And then of course I think that's all that it would take. So let's see, if we press start, we should expect the siren to come on. Okay, so there's that. So we can even have our siren in this environment.